Welcome to the Night Library. Tonight we'll be discussing cold weather. Section 1. Cold weather feels simple on the surface. You step outside and the air stings. Your breath shows up. Things that were flexible feel stiff. Your hands lose their precision. Sound carries farther. Time feels slower. But cold isn't actually a thing moving in the world. Nothing new arrives. What's happening instead is a quiet subtraction. Cold weather is what we experience when heat leaves faster than it's replaced. Heat, in physical terms, is energy stored in motion. Not motion you can see, like wind or falling snow, but motion at the scale of atoms and molecules. Tiny vibrations, jostling, sliding past one another. When something is warm, those particles are moving more vigorously. When something is cold, they are moving less. Temperature is just a measure of that motion. Higher temperature means more average motion. Lower temperature means less. So when the weather turns cold, the air around you hasn't gained anything. It has lost energy. The environment has become a place where motion drains away. That matters because nearly everything around us, our bodies, our tools, our buildings, depend on a steady flow of heat to behave the way we expect. Your body, for example, is constantly generating heat. Even at rest, chemical reactions inside your cells release energy. In mild conditions, that heat leaks out slowly and you barely notice. In cold weather, the leak accelerates. The surrounding air pulls energy from your skin faster than your body can comfortably replace it. That's why cold air feels sharp rather than gentle. It's not the presence of something harsh, it's the speed of loss. Wind makes this more obvious. Moving air strips away the thin layer of warmth your body builds near its surface. With that insulating layer gone, heat drains faster still. And this is why wind chill doesn't describe a new temperature. It describes a faster rate of heat removal. And the same logic applies to objects. Metal feels colder than wood at the same temperature because metal conducts heat more efficiently. When you touch it, energy rushes out of your skin and into the metal. Wood slows that transfer so your skin keeps more of its heat. The metal isn't colder in an absolute sense, it's just better at taking warmth away from you. Cold weather turns heat transfer into the dominant force in everyday life. It decides what feels solid, what feels fragile, what lasts, and what fails. Water is a good place to see this. As water cools, its molecules slow down and draw closer together, up to a point. Just above freezing, liquid water reaches its maximum density. Below that, as it becomes ice, the structure rearranges into a more open lattice. The molecules lock into place with more space between them. That expansion is why pipes burst, rocks crack, and roads buckle. It isn't freezing itself that causes damage. It's the change in structure, the way water takes up more room when it stops flowing. Cold weather, in this sense, isn't just about temperature. It's about phase. Liquids turn rigid. Flexible materials stiffen. Lubricants thicken. Chemical reactions slow down. Batteries struggle in the cold because the chemical process that move charge through them depend on molecular motion. Lower the temperature and that motion becomes sluggish. The battery hasn't lost energy, it just can't deliver it as quickly. Sound behaves differently too. Cold air is denser. and temperature layers can bend sound waves back toward the ground instead of letting them dissipate upward. This is why distant noises, traffic, voices, a train horn, can seem unusually clear on cold nights. Even time feels altered, not because it is changed, but because cold reduces activity. Fewer insects, fewer people lingering outside, fewer spontaneous movements. The world enters a lower energy state, and perception follows. What makes cold weather so noticeable is that it reveals how dependent we are on continuous motion. We live most of our lives in a narrow thermal window where materials behave predictably, bodies self-regulate easily, and energy flows are mostly invisible. Cold pushes us toward the edge of that window. It doesn't introduce chaos, it removes the buffer. In cold conditions, the rules become easier to see. Heat always moves from warmer to cooler regions. Motion always slows as energy drains away. Structures become more rigid when movement is restricted. Systems that rely on flow of electrons, of fluid, of air, become vulnerable. Cold weather is the environment reminding everything to conserve. In the next section, we'll look more closely at how different materials respond to that reminder, and why some things survive cold easily while others fail suddenly, even when the temperature change seems small. Section 2. Once heat becomes scarce, the world starts sorting itself by how well things hold together without motion. Some materials tolerate cold easily, others fail abruptly. The difference usually comes down to whether a system depends on flexibility, flow, or continual rearrangement. Take rubber as a simple example. At moderate temperatures, rubber molecules are constantly moving past one another. They stretch, recoil, and absorb stress by redistributing it. In the cold, that molecular motion slows. The material doesn't just become firmer, it loses its ability to rearrange internally. What was elastic becomes brittle. A rubber seal that works perfectly in October can crack cleanly in January. The same principle applies to plastics, adhesives, and many composites. Cold doesn't weaken them in a gradual way. It removes their capacity to adapt. Metals behave differently. Their atoms are already locked into a rigid lattice, so losing heat doesn't change their structure as dramatically. But metal still contracts as it cools. When different parts of a structure cool at different rates, an outside surface cooling faster than an inside one, stress builds. Over time, or with repeated cycles, that stress finds a release point. A fracture forms, a joint loosens, a fastener works itself free. Cold is especially unforgiving to systems made of mixed materials. Wood and metal shrink at different rates. Glass and steel respond differently to temperature changes. Even when everything is within tolerance, repeated cold cycles slowly pull assemblies apart. This is why winter maintenance exists as a category of work. It's not about extreme temperatures, it's about repetition. Freeze, thaw, contract, expand, slow, resume. Each cycle is small, but the damage accumulates anyway. Living systems face the same problem, but with different strategies. Plants, for example, can't generate heat in the way animals do. Instead, they manage water. Many species reduce the amount of free water inside their cells before winter arrives. Less water means less internal ice formation. Some plants even allow extracellular ice to form while keeping the inside of their cells protected. Insects often take this further. Certain species produce natural antifreeze compounds that lower the freezing point of their internal fluids. Others allow themselves to freeze solid, suspending metabolism almost entirely until temperatures rise again. Cold weather doesn't kill life by default. It selects for methods of waiting. Animals that remain active rely on insulation and behavior. Fur traps air. Fat stores energy. Burrows in snow itself create stable thermal environments. Snow is a surprisingly effective insulator, precisely because it traps pockets of air and slows heat transfer. This is one of cold weather's quieter lessons. Stillness can be protective. Air that doesn't move insulates better than air that does. Materials that don't change shape under stress. Materials that don't change shape under stress fail less dramatically than those that must flex. Systems that can pause survive conditions that would destroy systems forced to operate continuously. This is also why cold affects machines so strongly. Engines struggle because fuels don't vaporize as easily. Oils thicken, increasing friction. Clearances designed for warm operation tighten as components contract. What worked smoothly at room temperature now resists motion at every interface. Nothing is wrong with the machine. The assumptions it was built around no longer hold. Cold weather exposes assumptions everywhere. It shows which systems rely on speed, which rely on flow, which rely on flexibility. It makes visible the quiet dependencies that usually go unnoticed. Even our perception of comfort follows this pattern. Cold doesn't just feel unpleasant because of temperature alone. It feels unpleasant because it narrows the margin for error. Small exposures matter. Small delays matter. Forgetting gloves matter. Standing still matters. In warm conditions, the body can recover easily. In cold conditions, recovery costs more energy than it provides. That imbalance is a defining feature of cold weather. It's not that energy disappears. It's that energy stops circulating freely. It pools, drains, thickens, and slows. The world becomes less forgiving of inefficiency. And yet, cold also simplifies. Process is slow enough to observe. Sounds travel cleanly. Mechanical systems reveal where friction lives. Materials announce their limits without much ambiguity. You can often predict failure before it happens just by noticing what has stopped moving the way it should. In that sense, cold weather acts like a diagnostic environment. It strips away excess motion and leaves behind structure. The next time you step into cold air, notice what changes first, not just in your body, but in the world around you. Which things grow quiet? Which things stiffen? Which things suddenly feel fragile? And those aren't random effects. They're the visible edge of how matter behaves when motion becomes precious. Cold doesn't add drama to the world. It removes slack. And in doing so, it shows what everything is really made of.